Hi everyone, now we are going to solve a basic problem on a rankine cycle. So we can see here a problem, we can read the question in the screen. So rankine cycle, the steam in a rankine cycle, the steam inlet to turbine is saturated. So it's a very important point, take a note of this, saturated at a pressure of 35 bar. So the pressure here is 35 bar. The pressure of 35 bar is the pressure inside the boiler and exhaust pressure is 0.2 bar. So the pressure at zero point 0.2 bar is the condenser pressure. So we need to calculate turbine work, pump work, Rankine efficiency and condenser heat flow. Assume a mass flow rate of 9.5 kg. This is yum. So we can take a note of P1 is equal to 3.5 bar, P2 is equal to zero point 0.2 bar. So this is the boiler pressure, this is the condenser pressure. And the mass M is 9.5 kg per second. So, before solving this problem, we should understand a basic principle of a Rankine cycle. So, in a Rankine cycle, you can see there is a boiler, pressure is 3.35 bar. So, the, the steam enters the turbine at 35 bar, it condenses to a pressure of zero point 0.2 bar. Then, after it condenses, the vapor gets converted into liquid, and the liquid is pumped to a 1 to 2, that is again from a condenser it is pumped into the boiler. So we can draw a basic layout of a Rankine cycle. So a basic layout of a Rankine cycle looks somewhat like this. So it is a almost this diagram will be same for a Rankine cycle, basic simple Rankine cycle. So we'll name it as 1 1 1. It is a inlet of a pump pressure, outlet of a pump pressure. This is 3 is an inlet of a steam. Then 4 is the outlet of a turbine. 3 is an inlet of the turbine. 3 is the inlet of a turbine. 4 is the outlet of the turbine. Now we will try to find the enthalpy at 1, 2, 3 and 4. To find the enthalpy, we will begin it from basic step of state 1. So this is a state 1. So state 1, you can look at the diagram. 1, it is the pump inlet pressure. So to find the pump inlet pressure, you need to understand what is the condition of a state 1. So condition of the state 1 is a P. It is a saturated liquid. We know that this is a saturated liquid line, this is the saturated vapor line. So this is a saturated liquid. So obviously H1 must be HF. HF. So HF is what is the pressure at H1? H1, the pressure at the condenser is zero point 0.2 bar. Zero point 0.2 bar, we know that H1 is equal to HF because the zero point 0.1 lies on a saturated liquid. So all the the state of the working fluid, that is it must be it is completely in a liquid form. So at a zero point 0.2 bar, so at a zero point 0.2 bar, 251.5 kilojoule per kg. So how did we come to know? So through a steam table. So through a steam, so we can look at the steam table here. There is a absolute pressure, this is a pressure based chart, this is a pressure, saturated temperature, this is an specific enthalpy, enthalpy of the fluid, this is enthalpy of the fluid, enthalpy of latent heat of uh, latent heat of fusion, or latent enthalpy, that means enthalpy of a saturated gas. This is entropy of a fluid and entropy of SFG. This is entropy of a gas. This is volume of a fluid, volume of a gas. So we look through the pressure. We know what is our condenser pressure. Our condenser pressure is zero point 0.2 bar. So we look at the zero point 0.2 bar. So at zero point 0.2 bar, you can look what is the HF, because our fluid is in complete in a
our steam is a liquid form. So it is in a saturated liquid form. So we take it as HF 251.5 kilojoule per kg Kelvin. So we take a note of this. So we need note down the value of HF. HF is nothing but H1. So we have found H1. So now we next we need to find the H2. To find H2, before finding H2, we will find the pump work. Pump work is nothing but the amount of work required to pump the liquid from a condenser to into the boilers from one point to point number two. So we can look here to find the work done by the pump. We have formula Vf into P2 minus P1 into 100. The 100 stands for conversion of work because our pressure is in bar. Convert pressure in bar to kilopascal, you multiply it by 100 so that it becomes kilopascal. The final it will give rise to unit of kilojoule per kg. So next we don't have the value of Vf. How to find Vf? Again, to find Vf, we know that what is our state of the fluid. It is at a state 1. We know completely at a state 1 the steam is in a liquid form. When it is in a liquid form, V1 becomes equal to Vf at a point 2 bar. So V1 is equal to V2. Sorry, V1 is equal to Vf at a point 2 bar. So to find what is the value of Vf, volume of a fluid at point 2 bar, we need to look at the chart. We look at the steam table, so we can so see at a point 2 bar what is the volume of the fluid. So we see along the x-axis point 2 bar. We look along this axis here. You see it is a 0.0010, and so we take a note down this value 0.0010102 meter cube per kg. So we know 35 bar boiler pressure, point 2 bar pressure of the condenser into 100, and the volume of the fluid we get a pump work. So we know that the alternate formula for pump work is H2 minus H1 because the fluid is being pumped from 1 to 2 stage. So it is H2 minus H1. So we already know the pump work 3.539. So 3.539 is equal to H2 minus 25155. We know how we find from the thermodynamics data handbook. So we found finally we find H2 255.063 kilojoule per kg. Next, we need to find the next state, that is H3. So to find H3, we know where does the point 3 lie? The point 3 lies on a saturated vapor line. How did we come to know it lies on a saturated vapor line? We know from the question. The most important point is saturated. That is, inlet to the steam inlet to turbine is saturated. So that's why point 3 lies on this line. So whenever it is purely a saturated vapor, what should we do? We can note down directly H3 is equal to Hg. That is, we can go to our thermodynamics data handbook. So look here, pressure based chart. So we are going to find Hg. Why Hg? Because our point number 3 lies on the saturated line. So whenever it is completely a saturated vapor, the enthalpy value becomes equal to Hg because it is completely in a vapor form, and hence whenever something is completely in a vapor form, we can directly note down H value, and the given H value here it is H3 is equal to Hg. So we know that our boiler pressure is 35. So when boiler pressure is 35, Hg value is 2802. That is our Hg value. We take a note of it. After noting it down, we write H3 is equal to 802.0 kilojoule per kg. So we know H3 is equal to H3, and we came to know directly from the data handbook. Now we need, our aim is to find H4. So to find H4, we need to use the formula H4 is equal to HF plus X into HFG. Why did we, why do we need to calculate this whole thing? Why can't we directly note it down from the
data because we can look here. Where does the 4 lie? 4 lies in a under the dome, under this curve. So here the liquid, it is neither a liquid, neither a completely a vapor. It is a liquid plus vapor region. So we need to know the dryness fraction of at a state 4. So to find the dryness fraction, so we need to find HF plus dryness fraction plus HFG. HF and HFG can be found directly from point 2 bar. HF and HFG can be noted down from data handbook, but to find X we need to follow certain procedure. That is, we need to find entropy. So we know that at whatever lies at point 3, it is equal to S3 is equal to Sg. So at a 35 bar at a boiler pressure. So we again go to a thermodynamics data and from thermodynamic data output, our S3 value is completely a saturated vapor. So S3 is equal to Sg. So at a 35 bar pressure, we note down the value of Sg 6.1228 kilojoule per kg Kelvin. Now, after noting down the value of entropy, that is S3, we know that S3 is equal to S4 because in a, it is a 3 to 4 is a isentropic expansion. So isentropic in an isentropic expansion 3 to 4, the S3 is equal to S4. The entropy remains constant. S3 is equal to S4. But S4 is not completely neither completely a liquid neither completely a vapor. It is a mixture of liquid plus vapor. So we cannot directly write the value of S4. So we need to write whenever it is under the curve SF at zero point 0.2 bar plus X into SFG at zero point 0.2 bar. So we need to go again to thermodynamic data handbook and find the value of SF and SFG at zero point 0.2 bar. So we can look here at a note down the values of SF and SFG at a zero point 0.2 bar. So at a zero point 0.2 bar, SF value is, you can look here, SF value is 7.0, SF value is, sorry, SF value is 0.8321 and SFG value is 7.0773. So we note on SF and SFG values. After noting down the SF and SFG values, we substitute in the formula. We already know S3 is equal to Sg from thermodynamic data. We have noted down. Next, we are noting down SF with SFG. Now, take this at the LHS and find the value of X. So, after finding the value of X, we got the dryness fraction. X is nothing but the dryness fraction. So, dryness fraction is equal to 0.7475. Now we can calculate H4. We know that H4 is equal to HF at zero point 0.2 bar plus X into HFG at zero point 0.2 bar. So we can find, we can again go to thermodynamic data and note down the value of HF and HFG at zero point 0.2 bar because 0.2 bar because H4 lies in a it is an inlet to the condenser. Whenever something is inlet to the condenser, we have to use the zero point 0.2 bar. So we can look at zero point 0.2 bar. Zero point 0.2 bar, note on the value of HF and HFG. So at a zero point 0.2 bar, HF value is 251.5 and HFG value is 2358.4 kilojoule per kg Kelvin. So after noting down the value of HF and HFG from thermodynamics data handbook and we already know the value of X, we find H4. So H4 we have calculated. Now we are able to find the value of enthalpy at H1, enthalpy at H2, enthalpy at H3 and enthalpy at H4. Now we can proceed and calculate the turbine work, pump work, rankine efficiency and condenser heat flow. So we'll move forward. So first point is turbine work. You know the turbine work is equal to H3 minus H4. So if you look at the diagram, so looking at the diagram, turbine work is H3 minus H4. Pump work is H2 minus H5. So Rankine efficiency is what? Turbine work minus pump work divided by heat input. What is heat input? H3 minus H2. And so by substituting the value of H3 minus H4, we get turbine work heat input is H3 minus H2, then heat output is H4 minus H1. So we know that Rankine efficiency can be calculated by Rankine efficiency is equal to 1 minus Q output by Q input. Heat output by heat output by heat input. That is, heat output is H4 minus H1. H4 minus H1. This is heat output. Then H3 minus H2 is heat input. So we will substitute H4, H1, H3 and H2 so that we can get the Rankine. Here we have substituted the heat input 2546 here in the denominator and heat output 1763.07 kJ per kg in the numerator. So we get the efficiency of Rankine thermal efficiency of 30.77%. So this is one method of calculating the Rankine efficiency. You can also calculate the Rankine efficiency by using another formula. It's similar one. So W net, what is W net? W net is work of the turbine, work of the turbine, work of the turbine minus work of the pump. W net is work of the turbine minus work of the pump. So this is work of the turbine minus work of the pump divided by the heat input. Similarly we get 30.77 efficiency. So we can use both the formulas to calculate the Rankine efficiency. Next we need to find the condenser heat flow. To find the condenser heat flow we need to what is the formula? It is m into h4 minus h1 here h1. So where is the heat flow? Heat flow is here h4 minus h1. So we can similarly we can write the formula as condenser heat flow in kilowatts is equal to mass is mass flow rate of the steam into h4 minus h1. We know the h4 and h1. So we calculate we get 16749.16 kilowatts. Next we can find the Carnot cycle efficiency. We know that to find a Carnot cycle efficiency, we know the Carnot formula, that is eta is equal to 1 minus T minimum by T maximum. The problem here is we don't have T minimum and T maximum values. To find T minimum and T maximum values, we can use P2 and T2. The P2 pressure of the condenser and pressure of the boiler. So we know that pressure of the boiler is in the top part of the ranking. So we look here. So you can look here. 35 bar is the temperature of the maximum T max. Where does the lower temperature lie? Temperature is lower in the pressure in the condenser, that is 0.2 bar. So this is, if you can use 35 bar to find the temperature T max and 0.2 bar to find the T minimum. So maximum temperature and minimum temperature can be found by using 35 and 0.2 bar. So how to find it, we will look. So you can look here at a 35 bar, we can find the saturated temperature of a steam at 35. How to find it? We have to go through the thermometer. In a pressure based chart, you can look here. There is a absolute pressure and there is a saturated temperature. So for pressure in the boiler is how much? 35 bar. So at a 35 bar, what is the saturation temperature? 242.5. So this is the maximum temperature. So we can note down for a 35 bar, this is the saturated temperature. So next is we need to find the temperature, saturation temperature in the condenser. What is the condenser pressure? It is 0.2 bar. It is 0.2 bar. So what is the saturation temperature? For 0.2 bar, it is 60.1. So this is T minimum. That is minimum temperature is 60.1, and or what is our maximum temperature? The maximum temperature is 242.5. We need to convert it into Kelvin. Plus 273 plus 60.09, 242.54 plus 273. Okay, so we convert them into Kelvin because for a formula, Carnot efficiency formula, we need to have the values in Kelvin. So 1 minus T minimum by T max. So T minimum is 33.09 and T max is 515.5. So we got a Carnot efficiency of 35.39. So we can look here, our Rankine efficiency is lower than that of the Carnot efficiency, that is 30.77% is less than 35.39. Why? Because no engine or no heat engine can be more efficient than the Carnot engine. So this is the end of the problem. So we'll give another similar problem for the assignment which you have to solve and submit.